Hi, everybody. I'm Jim Cotton from McMaster University. I'm the co-director of the Institute of Energy Studies, and I'm representing a cooperative of partners, 20 partners actually, in our community in Ontario that I've been working with for the past 5 years on integrated community energy and harvesting systems. And I talk a little bit about the value of waste heat, and I don't use that term very much anymore. But the session is about waste heat. I talk about energy harvesting. This is a resource that's within our community that we need to understand and use. So climate action requires certain actions that we need to start taking. And Peter mentioned them right off the bat is our buildings have significant carbon, 20 to 40%, depending on the type of building. In Ontario, we live in a very cold climate. Right now, it was -20 last night or so. And the solution could be the electrification of heating. But what does that bring into play? That brings into play a 2 to 5 times increase in electrical demand. And that depends on how you do it. And I'm going to talk a little bit about that. So that is happening at the same time as we're electrifying vehicles. But another problem is we waste more energy, more of our primary resources to the environment than we actually use. So if we start to think about how to integrate this and look at these challenges together, we have actually a pretty good solution towards tackling this problem. And this is a slide just to give you an idea of where we are and where we're going. Okay, so the black line here is our electricity consumption in Ontario. Okay, it peaks in the summertime. The red area here, that's our heating demand. It's cold. Our heating demand far exceeds our electrical demand. Now, if you look at our peak electrical demand, it's about 80,000 megawatts. And that's sort of those days when we have -30, -40 degrees Celsius. Compare that to our peak, summertime peak, we're at 23,000 for the last few years, right? Now, let's electrify heating, okay? And I'm not going to get into this too much, but we have different COPs. So here's our average COP for, say, an air source heat pump with a seasonal average of 2. Here's an average COP of 3. So this would be a typical installed ground source heat pump. And then here's a higher one, a COP of 7. So if we used waste heat resources, what would happen? Now, that's a challenge. It's a huge challenge in itself to increase our electricity capacity up to 50,000. But the real challenge is increasing our peak. Okay, so if you look at the coldest day of the year, how is a heat pump, an air source heat pump, going to perform? It's going to have a COP of 1, essentially our electrical resistant heating. We have now almost have a 5-fold increase in terms of our peak winter demand. So this is a challenge we have to address and understand. It's not just the amount of energy, it's the peak energy that we have to start thinking about and addressing, and we have to do that now. So, by the way, this doesn't include EVs. So here, there's an issue here is we're doing this across all sectors. This doesn't include industry. So what happens when we include all of that? Well, the other thing is we waste. We waste a lot. This is Ontario. This is sort of old right now. Unfortunately, Caesar doesn't update their visualization reports anymore, which is really sad. But if you go back 2013, it hasn't changed that much aside from this gray line of coal. It's completely gone out of our energy sector. We basically used of primary resources 4,000 pentajoules. Okay, what does that mean? That's 100%. Let's just keep it at 100%. We used about 33% of that. Okay, the rest was lost to waste heat. So if we look at that and we break that into sort of numbers and give some relationships, those Zinke diagrams, essentially, if we were able to reuse some of that waste heat, what would that mean? How much is it? What is available? We need to start mapping this. This was done from a top-down approach with our research partnership on the Ice Harvest project. And it gives you an idea of the total waste. So if you look at from industrial waste, it's definitely the highest opportunity. Okay, so it's commercial. So we're talking 64 terawatt hours of thermal energy, 30 terawatt of thermal energy. And in our study, actually, we focused on these ones because these are going right into our community. These are directly assets that we can use right now and start to decarbonize our heating using these wasted resources. You sum all of this up, and we have 130 plus terawatt hours of wasted energy already embedded in our community. And our heating from natural gas right now is about 191. You're talking right there. If we could harvest 50% of this, just 50%, you're reducing that carbon emissions and going directly to our targets, essentially exceeding our targets by 2030, 2035. So first off, what you would do, and this was highlighted in the industrial waste heat recovery project by HCE and Taft and the Chamber of Commerce, is the high quality, good energy you use on site. And I went back to when I started at Mac, and I remembered this paper, and I remember these payback periods. And I don't know if you remember, in Ontario, gas used to be expensive. 43, this is the commodity price, 43 cents. We've been averaging from 2010 to 2020 about 10 cents. And these were the payback periods. Okay, so 1 to 2 years, about as high as 3 years for some. Most of them just simple heat recovery projects. It's a heat exchanger and some pipes. That's what it is, maybe a pump. So it makes perfect sense. Now, this payback period got a little bit worse. And I did some projects with some big industry partners in Hamilton. And these numbers started to creep up to 2.5 to 3, and it was harder to do. But what we did is a full energy balance on the entire plant. And what we found was, yes, there's high quality energy with good payback periods. And what really incentivized them was not the payback period, because the huge capital cost up front for some of these projects, but what it was the increase in productivity that led to better resources allocations, better quality in terms of their products. That's some of the things you could do with heat recovery. One thing we did for a strip mill was we investigated preheating their ingots before they went into the furnace. So instead of keeping them and letting them cool down, keep them at 200, 300 degrees Celsius. Right off the bat, it's about between 15 and 20%. Good payback period, about 3 years. But what really started to sell them on that was the increase in quality, the increase in productivity. And in fact, they hired the student that was working on that project to continue working there. Another one I'm going to plug is my own company. So look at the commercial side. Think about how much we waste. And this is far worse than any other process that we talk about. Look at our cooking processes. Pizza, for example, is the company we partnered with, and they waste 90% of the natural gas. So 50 cubic meters of natural gas a day, every day, summer, winter, fall. And 90% of that goes up the chimney. We've developed a system that integrates their electrical system, their hot water system, and we even preheat the air going to the system. We've reduced the consumption to about 43, and now only 40% of the waste goes up the chimney. This has a payback period of about 2 to 3 years. Okay, and this is 2 to 3 years of a prototype costing, so not commodity costing, not high volume costing. Still a challenge for them to do. But what we've proposed now is a rental energy sharing model. And this is really taken off. So we look at this, we have a 10 to 15 year lifespan of the product. If we are able to install it for free, this is something that they really think is going to happen. And this is servicing markets that typically can't afford high quality, high expensive materials to do this energy harvesting. Now, what is motivating this? Well, we don't have the same problems as Europe. Our cost of natural gas is fairly inexpensive. And the number I showed you before, the 2006 numbers with the sort of 1 to 2 payback period, we're only now in 2025 going to be hitting that. And that's really thanks to a carbon tax. So if you're stressed about a carbon tax, just go think about 20 years ago, before fracking, and the cost of energy then. Here's our projected carbon tax. Here's our delivery charges with inflation. Here's our projected natural gas commodity costs. It's not expected to go up much. Here's our HST. Thank you. And here's another price on carbon. So we're looking at right now essentially doubling the cost from where we are in 2030. And we have some significant motivation. If you think about a 1 year payback period in 2025, using the 2006 numbers, we're getting into fractions. So right now, it just makes sense to do that. But this also has implications on our home heating systems. And if we want to look at this and really target carbon emissions reductions, we have to think about how to do that. And I'm going to give a very brief introduction. Many of you probably have seen presentations from me on the ice harvest system. It's a distributed energy resource. It's essentially, we call it a microthermal network. It's an integration of multiple DER assets, so heat pumps, CHP systems. Right now, we're using natural gas. In the future, we could use solid oxide fuel cells that run and have carbon capture, still on natural gas. We could use other technologies, biomass generation. But the primary focus of this is the energy harvesting. Now, one thing I didn't mention in my studies when we did some of the industrial partners in Hamilton, even with the increase in harvesting on site, the reuse of the high quality energy, they had more energy they could ever use. So why wouldn't they try to sell that or get carbon credits and give that to the community to reduce the community's energy harvesting potential? And that's sort of where we're going right now. We also need controllable loads. And I'm not going to talk much about that, but as you get more renewables, you get more curtailment. And essentially that's electricity that we don't even, doesn't even reach the wires. And I think ultimately there's a huge benefit of bidirectional vehicles and all of this. But the objective really is to minimize greenhouse gas emissions. And I'm going to say that's really the opportunity. So this is a rendering of the ice harvest system. It's very similar to a fifth generation district energy system. It is much smaller. And the key difference is that we vary the temperature of the system. And therefore, by varying the temperature of the system, we can fuel switch on the fly within 15 minutes to half an hour from running a CHP system, say as a decentralized peaking power plant, and run this, say, during the day, like we do right now, following the grid requirements, not the site requirements. So you're offsetting central peaking power plants that are 42%, replacing that with something that is 80% or higher efficient, and delivering heat through a microthermal network. Now, these our goal is to export energy so we can support the rest of the community high intensity loads, especially as we start to electrify our vehicles and geothermal systems in the neighborhoods around us. So we could store some of this energy in short term. And then at night, when we turn off our CHP, what we would do is reduce the temperature of the system and then electrify heating using heat pumps. And these heat pumps, they could be bidirectional. Say for an arena that is constantly dumping thermal energy, we could be capturing that and putting it into our system. Okay, so we do direct heat exchange during the day, get rid of electricity. Heat pumps at the day increase the electricity from 2 to 4-fold. So now we have control. We're creating these loads. This arena could share energy with the pool next door. Or we have this community center. Community centers or libraries, they have data centers. We'll integrate the data centers. And maybe there are certain times that they are using energy to heat the building, or internally they're taking the energy from their data center, their waste heat, and heating the building. But if there's too much, give it back to the community. This is great in the wintertime, but what do we do in the summertime? Well, we have and have built the system is seasonal storage. And at McMaster, we have a 66 borehole thermal storage system. It goes down 7 stories, 30 meters in diameter, and we actually heat up the ground to 60 degrees Celsius during the summertime. Wintertime, use that heat directly during peaks. Now it's starting to reduce, if you manage this property, this peak minus 40 degrees, minus 30 degrees Celsius day, and start to really integrate our different systems. And we're trying to replicate this. We've actually realized and this is really not even focusing on industrial waste heat, just to be clear. 1,000, like 1,100, I guess, 1,100 sites across the communities, focusing on big box stores, condo intensified areas, so apartments, restaurants, and community campuses across the province. Here's an example of a community campus. It's only 4 buildings, maybe 5, because we know that they're going to be building a couple of condo towers just down the street. The diameter is less than 1 kilometer and about 1.5 kilometers if you include the condo tower. We have an arena that's dumping energy. We have a library that's dumping energy all the time, the cooling towers. Okay, so if we just put this microthermal network in play and we integrated this, what happens? Well, your business as usual carbon emissions is about 2,200. If you just start sharing energy, just from those two buildings, it goes down to 1,300. We add a CHP system, and we operate that CHP system as a peaking power plant. Okay, and we can play with that. Okay, we do it behind the meter, or we do it in front of the meter. We're reducing that down to 8,000 or 870. Now we go one step further. Let's add seasonal storage. Now we're down to about 65% business as usual case. If we look at all of these sites in Ontario that we've identified through publicly available data, not even including industrial waste heat, just to be clear, we basically can reduce carbon emissions by 2.1 million tons. That's a significant amount. So this 65% less than business as usual. And if you look at our targets to 2030, that's completely doable. Now, how much is that? It's about 2 gigawatts of installed capacity, and they're on average about 1 megawatt size systems. It seems a lot, but that has already happened over the last 15 years in Ontario. We have CHP systems running 24/7 behind the meter, essentially, doing the same thing. Now, the next phase of our research project is really looking at mapping the additional opportunity around waste heat. And this is a study. Sorry, I have to put the reference on it. I forgot, or it didn't. It's not on this slide, but I'll have that in the slides when they're available, from Rotterdam, Netherlands, and I love it. It takes forever to explain it. Something I want to do eventually, but essentially this is your heat map. So the blue is the demand, okay, and then they're looking at opportunities for non-carbon based. So we have solar thermal roof collectors. They're looking at road collectors. They're point sources, and then geo exchange systems, all mapped to the city. And then looking at suitable storage. We need to start doing this in Ontario. We need to map out, in particular, our point sources and our loads and show where these networks belong. They don't have to be monstrous district systems. We have a built city, but if we started doing these microsystems, eventually they will connect. So the ice harvest system is actually a grid modernization asset, not necessarily a district energy system. It focuses on harvesting, it focuses on sharing, focuses on electrification, but it's really a DER asset that I think should be controlled but as a grid level asset. And that really brings us into this distributed system model, operating model, where a lot of it is controlled by our LDCs. As we get more and more DER assets within our communities, they need to be managed. And I think the most logical is through a distributed system model operator and our LDCs. It also provides resiliency. And I think there's going to be significant value to that moving forward. We've seen this in Western Canada, floods, fires. We've seen this in Burlington, so that's a key element. And then it provides auxiliary services, right? We're a dispatchable speed, dispatchable load. You have ancillary services such as power frequency control. So final remarks, energy harvesting is critical. So these thermal networks and realizing the opportunity to share your energy, which is, I know it doesn't really happen, sell your energy through microfinancial transactions, get carbon credits is key. I think we really have to step up our building code, and buildings need to be low temperature HVAC ready so they can harvest this solar energy, this waste heat recovery. That's something I've talked to everybody about lately. We really need a national energy harvesting strategy. We need to map this community waste. We have to realize it's a resource and bring it together. And finally, just as a personal note, back in December 3rd, they came out with the pillars of climate plan for 2030. And the pillars were essentially net zero electricity, net zero vehicles, oil and gas caps, and emissions. They completely left out the building sector. And as Peter said, this is 30 to 40% of our carbon emissions. I think it seriously undermines our ability to meet these targets if we don't really start focusing on addressing these goals. Now, last, I just want to thank the team. We've had over 50 people work on this project, graduate students, postdocs, all the ones are highlighted are off in industry. Actually, I see a lot of the partners have hired these folks. They did all the real work, and finally, my industry partners. HCE in particular has taken a big leadership role in Grid Smart City. But to be honest with you, it is amazing. We have all sectors of energy delivery from district systems to thermal energy delivery partners, to geo partners and our LDC partners all work together to make this project happen. Thank you.